This is Richard Hammack's Calculus 1 course. We're in part 1 of the course, Function Review, and today we are reviewing inverse functions. And our plan is to talk about the idea of an inverse, to review one-to-one functions, to define inverses, talk about how to compute them, how to graph them, and then we'll discuss the idea of restricting domains, which will be useful for us soon. Here's the basic idea. Sometimes you'll have a function f, and you'll be able to come up with a related function called its inverse, or f inverse, which we're going to denote as f to the power of minus 1, and we'll read that as f inverse. The inverse of a function f is another function f inverse, for which f inverse of f of x equals x. In other words, you plug in the number f of x into f inverse, and you get out the number x. So in essence, f inverse is undoing the action of f. You plug in x to f, you get some number f of x, you take f inverse of that number, and it bounces x right back to you. It undoes what f does to x. You can think of it this way. Suppose you have a function f of x, and you take its graph. We'll talk about how to think of the inverse of f, how to think of f inverse from this graph. First of all, think about f. How does f work? Well, if you want to plug in a value of x to f and get an output, you can put x on the x-axis, move vertically to get to the graph, and then horizontally to the y-axis, and you arrive at f of x. So you can think about f as sending this x to the y value f of x. F inverse is going to do exactly the opposite of that. It's going to take this y value of f of x and send it back to x. It's going to reverse the arrows. F inverse sends f of x horizontally and then down to x. And it's undoing what f did to x. Whatever f of x was, it's going to send it back to x. Now typically you want to think about this number f of x as being just a regular value of x. Just call it x because it's what you want to plug into f inverse. So f inverse is going to take a value of x and send it to some value of y down here. Let's look at an example. Here is the function f of x equals the square root of x plus 1. So that's our f of x. Let's see if we can figure out f inverse of 2, f inverse of 3, and f inverse of 4. Let's start with f inverse of 2. So according to the picture that we have here, the input is going to be 2. We're going to put it on the y-axis and try to run f backwards. Notice that for this function, starting at 2 on the y-axis, going over to the function and down to the x-axis, you arrive at 1. And sure enough, if you plug in 1 to f of 1 is square root of 1 plus 1 is 2. So f sends 1 to 2. F inverse would send 2 back to 1. So f inverse of 2 equals 1. What about f inverse of 3? We'd look at what happens to 3 up here and where it goes. So 3 goes over to the graph and then down to 4. And you can check that because if you plug in 4 to f of x, this is square root of 4 plus 1, that's going to be 3. F sends 4 to 3, so f inverse is going to send 3 back to 4. F inverse of 3 equals 4. Finally, what is f inverse of 4? We look at 4 on the y-axis, we go over and down, and f inverse of 4 is 9. So one way to think of an inverse is this way, to summarize what we've been doing in this example. You can actually write a little word expression for f inverse of x to define it. F inverse of x is the number you plug into f to get x. So for example, F inverse of 3 is the number 4 you'd have to plug into f to get 3. We'll have more to say about this in a couple of slides. So this is the basic idea of an inverse. It's just running f in reverse. But this does not work for just any function. Think about the function y equals f of x that I've graphed here, and imagine you're trying to find its inverse. If you run it in reverse, take a point on the y-axis, a number here, go over to the graph, and then down to this point. Would that be f inverse of the number we started with? Well, actually, we're not sure, because you could also go horizontally over here to get this. So what is f inverse of this number? Is it this number or that one? The rule that we talked about on the previous slide just doesn't work for this function. And as you can see, the problem is, when you get right down to it, that you can find a horizontal line, shown here in red, that crosses the graph in two or more places. Because as long as you have that possibility, you're not going to know whether f inverse is going to send some value here to which number. So from this, we're going to make a definition. We really want to rule out this kind of behavior. We say that a function is one-to-one if no horizontal line crosses its graph more than once. In other words, if this doesn't happen. So in other words, a function is not one-to-one if some horizontal line crosses its graph in two or more places, like in this picture. So in essence, one-to-one functions are going to be the functions that are going to be good for us. They're not going to exhibit this pathological behavior that we had here that blocked us from finding the inverse. So for example, think about the square root of x plus 1. The function we had on the previous slide. Notice that if you take horizontal lines, either they'll cross the graph not at all, in other words, 0 times, or exactly once. So this would be a one-to-one function. No horizontal line crosses the graph more than once. Whereas y equals x squared, there's a horizontal line crossing more than once. In fact, there are lots of horizontal lines crossing more than once. So this is not a one-to-one function. So the idea here, the important point, is that for a function to have an inverse, it's got to be one-to-one. With that, let's move on to the definition of the inverse of a function. And here is a fact that you should know from precalculus. If f is a one-to-one function, then f has an inverse, f inverse, for which f inverse of f of x equals x. And you think of it just as we motivated a few slides ago. Given the graph of f, to get f inverse, you essentially run f in reverse. From a y value, what is f inverse of that y? You go over to the graph and then vertically to the output for f inverse. So f inverse of f of x equals x. F inverse is undoing what f does. And if you think about it, also f of f inverse of x will equal x. So if you take f inverse of a number x first, and then take f of that, you get right back where you started. So the thing about an inverse, f inverse of f of x equals x, and f of f inverse equals x. So f and f inverse undo each other. So here's the picture for f inverse. What is f inverse of x? You take a x right here on the y-axis, which is an output value for f. You go over to the graph and then vertically to the x-axis to get your output y equals f inverse of this x. So you can think of a rule for the inverse as being this. F inverse of x is the number y for which f of y equals x. F inverse of x is the number y down here for which f of y equals x. And often using this rule that's in the box, this rule for an inverse, you can reason out function values for inverses. We'll look at an example of that, but there's one more thing I want to say on this slide. Let's talk about the domain and range of inverses. Notice that for f inverse, any input value actually had to be an output value for f. So f inverse could send it right back. So the input values, the things you're plugging into f inverse, they're all the outputs of f. In other words, they're the range of f. So the domain of f inverse is the range of f. And likewise, the range of f inverse would be all of the output values for f inverse, and they're down here on the x-axis. They're things you could plug into f. So they're the domain of f. The range of f inverse is the domain of f. So notice that f inverse has a domain and range that's exactly the opposite of the domain and range for f. The domain of f inverse is the range of f. The range of f inverse is the domain of f. So internalize everything that's on this slide, and we'll move on. Here's an example. Consider the function f of x equals x cubed plus 2 to the power of x. And if you think about it, this really is a one-to-one function because x cubed is an increasing function. As x increases, it increases, as is 2 to the x. So if you add them together, you get a function that just gets bigger and bigger and bigger and bigger. As x gets bigger, it's never going to go back down. So you're never going to be able to go up and then back down to reach the same y value that you had previously. So you're not going to get a horizontal line crossing this. So this is a one-to-one function, so it should have an inverse. And we're going to see if we can reason out f inverse of 1, f inverse of 3, f inverse of 12, and f inverse of 10. Now, remember here, the rule for f inverse from the previous slide, f inverse of x is the number y for which f of y equals x. You might think about that as f inverse of x is what you plug into f to get x. So let's go back here to f inverse of 1. According to our rule for f inverse of 1 will be the number y for which f of y equals 1. It's the number you plug into f to get 1. So we think about that. What number would we have to plug into f up here to get 1? And you play around with it for a while, and then you realize, oh, f of 0 would be 0 cubed plus 2 to the power of 0. That would be 0 plus 1, or 1. So f inverse of 1 would be 0. It's the number you plug into f to get 1. Let's try f inverse of 3. Again, f inverse of 3 is the number for which f of y equals 3. The number y for which f of y equals 3. It's what you plug into f to get 3. Looking at f, what would we plug in to get 3? Well, this is pretty easy. try one or two things and suddenly realize, oh, f of 1 is 1 cubed plus 2 to the power of 1. That's 1 plus 2, or 3. So the number y for which f of y is equal to 3 would be 1. You plug in 1 to f and you get 3, so that means f inverse of 3 equals 1. F inverse of 12 is the number y for which f of y equals 12, and let's do some reverse engineering up here. What are we going to do? Let's see. Well, if we plug in, we just tried plugging in 1. Let's try 2. F of 2 would be 2 cubed, which is 8, plus 2 to the 2. That's 8 plus 2, and that's 12. So if we plug in 2 for x, for f of 2, we get 12 out. So f inverse of 12 is 2. It's the number which, if you plugged it into f, you'd get 12. So these are pretty easy to figure out. Let's try f inverse of 10, and you'll suddenly realize this is not so easy. You're thinking of a value x that you plug into f, so the output is 10. And you try, let's say 3. That's going to be 3 cubed plus 2 to the 3. That's not 10. You try a bunch of other values, and you just can't get 10. Nonetheless, you may feel like f inverse of 10 might exist. It might be some number. It's just hard to compute. So from this simple rule for f inverse, it works for a lot of convenient values of x, convenient inputs for f inverse, things that are obviously outputs for f, but it's not really a way to calculate every inverse value. But it's important that this is a rule for f inverse. It's a way of thinking of inverses that's going to be very useful for you. So what you would like to do, now that you sort of have a facility for seeing and understanding inverses, is to be able to compute them. And this is something that you've seen before. Given an algebraic expression for f of x, find the algebraic expression for f inverse. So maybe you could compute f inverse of 10 like in the previous slide. And I'm going to motivate the procedure for computing an inverse like this. In our example, let's try to solve the equation y equals f of x for x. In other words, we want to isolate x. And imagine that this f is a one-to-one function, so it has an inverse. So if you want to get x by itself outside of the f, one thing you could do is take this equation, y equals f of x, and take f inverse of both sides of it. So on the left-hand side, you'd get f inverse of y, and on the right-hand side, you'd get f inverse of f of x. But we know f inverse of f of x is equal to x, so we get x equals f inverse of y. So we've successfully solved the equation y equals f of x for x. So this indicates that one useful thing about inverses is they can potentially solve equations. But there's something a little more significant about what we just did here. We started with the equation y equals f of x, and we solved for x, and we got x equals f inverse of y. And this suggests that if you ever have a function f, and you want to find out what is f inverse, just solve the equation y equals f of x for x, and you'll wind up with f inverse of y on the other side. And that gives us a consequence. How to find f inverse from f, provided f is a one-to-one function. This is a three-step procedure. You're going to mimic what you did up here. Start out by writing y equals f of x in step 1. Now the next thing you would do is solve that for x. Solve the equation y equals f of x for x. And as we saw up here, we get x equals f inverse of y. So you will get x equals f inverse of y. And there's your inverse. The only thing is, usually we like to think about x as being an input and y as being an output. So the last thing you want to do is swap those variables. Swap the x and the y to get y equals f inverse of x. So there we have it, a three-step procedure for finding f inverse. In some texts, you'll see steps 2 and 3 reversed. You can do them in either order. It's up to you. So let's take a really simple example here. Find the inverse of f of x equals 6 minus x cubed. And let's carry out our steps. The first thing we do is we write y equals f of x. Y equals 6 minus x cubed. That's what f of x is. Next, we're going to solve that for x. So let's begin to isolate the x term, add an x cubed to both sides, subtract a y from both sides. We get x cubed equals 6 minus y. And then we can take the square root of the cube root of both sides to isolate x. X equals the cube root of 6 minus y. So we've got x equals f inverse of y. The third step is to swap the variables. So y equals the cube root of 6 minus x. And so that's our f inverse. F inverse of x equals the cube root of 6 minus x. Now, whenever you do this, you can check it. Let's do that off to the side. How would you check to see if you have the right inverse? You've just found what you think is f inverse. To see if it's really right, do f inverse of f of x from the f inverse that you just computed. Because you should get x back if you do this. And if you don't get x back, then you did something wrong. But let's check it. So f inverse of f of x. We're doing this composition here. So the rule for f inverse that we've proposed is that f inverse of a quantity is the cube root of 6 minus that quantity. So f inverse of f of x is the cube root of 6 minus f of x. And then f of x was 6 minus x cubed. So plug that in, and we get the cube root of 6 minus x cubed. Distribute that minus in there, the 6's cancel. And you get the cube root of x cubed, and that's x. So we know we did it right. So you should refresh your memory of this technique and your skills with it by working some exercises. I picked one of the easier ones here to do in class, or to do in lecture. You want to make sure that you can do a variety of these. And as always, get practice. So finally, I want to talk about graphing inverses. Given the graph of a function f of x, the question is, what does the graph of f inverse of x look like? And we can think about it this way. If we have the graph of f of x, we know that if we plug in an x, you can go vertically to the graph and then horizontally to f of x on the y-axis. F inverse is going to send the f of x back to x. But we think about that f of x as being an input value for f inverse, which should be on the x-axis. So let's put this number f of x on the x-axis. It's right there. And we know that if we take f inverse of it, we have to get to x. Taking f inverse of f of x gets us to x. So plugging in f of x to f inverse gets us to x. So this point right here has to be on the graph of f inverse. So the graph of f inverse, whatever it looks like, passes through the point f of x, comma, x, because the graph of f passed through the point x, comma, f of x. Now, let's look at the geometry of this picture. The x value f of x right here and the y value f of x, which is exactly the same value, they form a square like this. And the two x values, x on the x-axis and the y-axis, they form a little square right here, including the origin. And you can run a straight line, 45-degree line, right up through those diagonal points. And this is the line y equals x. Y equals 1 times x plus 0, a line with slope 1 and y-intercept 0. Y equals x. And notice the relationship between these 2 points on the graphs of f and f inverse. You just reflect a point on the graph of f across that line, y equals x, to go to the other side the same distance, and you get to a point on the graph of f inverse. So the fact is that the graph of f inverse is the graph of f reflected across the line y equals x, as shown here. And that's how you get the graph of f inverse from the graph of f. So as an example, think about the graph of f equals x cubed plus 1. That looks like a one-to-one function, so it should have an inverse. How do we get the graph of its inverse? Draw the line y equals x and reflect f, the graph of f, across that line, and we get the graph of f inverse. And if you use the technique we talked about on the previous slide to find out algebraically what f inverse is, you'll find that it's the cube root of x minus 1. So there's always this really symmetric and beautiful relationship between the graphs of f and f inverse. One is just the reflection of the other across this diagonal line. So again, get some practice with this, and this is an idea that's going to come up a good bit in the next several lectures. It'll be significant. There's one more topic we should talk about, and it's the idea of restricting domains. And the idea is this. We know a lot of functions don't have inverses. Any function that's not one-to-one doesn't have an inverse. But there will be situations where you really want them to have inverses, but they're not going to have them. So the idea is, if a function has no inverse, then sometimes we can fix this by changing the domain of the function. So for example, think about f of x equals x squared. Its domain is all of the real numbers. And that's not a one-to-one function because a horizontal line crosses it twice. So it doesn't have an inverse. But it would be nice to have an inverse of the square function. So one thing we could do is we could say, well, let's fiddle with this function f of x equals x squared and fix the problem of it not being one-to-one by restricting its domain to say, oh, just the positive numbers, 0, the non-negative numbers. And that's essentially cutting off half of the graph, the path for which x is negative. So suddenly when you do this, of course you get a slightly different function because you've changed the domain, but notice that it's one-to-one, so it has an inverse. And you can reflect this graph, f of x equals x squared, across the line y equals x, and you get an inverse, f inverse equals the square root of x. So by restricting the domain of a function, you can sometimes get it to have an inverse. So as an example of this, an example which will be significant for us in lecture 6 is the graph of y equals cosine of x. Cosine of x is definitely not a one-to-one function because you can find horizontal lines that cross it infinitely many times. Yet, there are situations in which you would really like to have an inverse for this basic function cosine. So this is a little peek ahead. We're going to fix this problem of the function cosine not being one-to-one and not having an inverse by restricting its domain. Imagine that you erased all of the graph of cosine of x except this little part between 0 and pi. Just this part that's right there. And any horizontal line crosses that at most once. So that restricted cosine of x with the restricted domain is suddenly one-to-one. If we restrict its domain to the interval from 0 to pi, it has an inverse. So this idea will be significant later. So more on this later. That's it for today. Next time, we'll talk about lecture 5a. That's going to be a review of exponential functions. And then lectures 5b and 5c, where we talk about inverses of exponential functions. And these are things called logarithms. And this is very significant. Then we'll do lecture 6 on inverses of trigonometric functions, as promised. So coming up, the sequence of lectures that are going to heavily rely on what we talked about today. So work some exercises and make sure you can do it easily and you don't have any questions. Have a great day, and I'll see you right here next time. And goodbye.